All right, use the appropriate series to estimate the integral from 0 to 1/2 of x squared times e to negative x squared dx. All right, what I want to do is I want to start off by noting that e to the x is equal to the sum n equals 0 to infinity of x to the n over n factorial. That's the Maclaurin series for e to the x. Now this converges for all x, and you can quickly verify that if you want by using the ratio test. Because it does converge for all x, that would then imply that e to the negative x squared equals the sum n equals 0 to infinity of negative x squared, oops, let me fix that, negative x squared, there we go, to the n over n factorial, which is equal to the sum n equals 0 to infinity. I'm going to have a negative 1 to the n x to the 2n over n factorial. That would imply that x squared times e to the negative x squared equals x squared times the sum n equals 0 to infinity negative 1 to the n x to the 2n over n factorial, which is equal to the sum n equals 0 to infinity negative 1 to the n x to the 2n plus 2 over n factorial. This 2 right here is from my x squared. All right, that would then imply that the integral from 0 to 1/2 of x squared e to the negative x squared dx must be equal to the integral of the sum n equals 0 to infinity negative 1 to the n x to the 2n plus 2 over n factorial dx, which of course is equal to the sum n equals 0 to infinity of the integral of negative 1 to the n x to the 2n plus 2 over n factorial dx. And of course I skipped my bounds here. I need to put the bounds of integration on here, which is equal to the sum n equals 0 to infinity. Take the antiderivative of this. I will have negative 1 to the n x to the 2n plus 3 over 2n plus 3 times n factorial plus, I'm going to move it out here, some constant of integration. Okay? Well, actually, I don't need that constant, do I? Because this is a definite integral. I'm sorry. I fell asleep for a moment. Okay, now we need to evaluate this from 0 to 1/2. Well, notice at 0, this is easy. When x equals 0, I get an infinite number of 0, so that's 0. So I don't even have to worry about that. So all I really need to be concerned about is the 1/2. So I need to know is what's the sum n equals 0 to infinity negative 1 to the n 1/2 to the 2n plus 3 over 2n plus 3 times, whoops, times n factorial. Now notice I need to be accurate to within 0.001. Well, I'm going to rewrite this one more time. This equals the sum n equals 0 to infinity negative 1 to the n over 2 to the 2n plus 3 times 2n plus 3 times n factorial. And I think you can see by looking at this that this is clearly an alternating series. You can do alternating series tests and confirm that this does in fact converge by the alternating series test. That means to be within 0.001, I need the n plus 1th term to be less than 0.001. So what I'm going to do is I'm going to start writing out my terms here. this is going to be equal to, see, 1 over 2 cubed times 3 times 0 factorial minus 1 over, see, when n is 1, this is 2 to the 5th times 5 times, I said 1 factorial, plus 1 over 2 to the 7th times 7 times 2 factorial. And I'm going to stop there and say that this actually gives me, this should be approximately because I'm not going out forever, but this piece is actually equal to, and I worked this out a little bit earlier, 1 over 24 minus 1 over 160 plus 1 over 1,792. And of course this would keep going. But 1 over 24 is 0.04166 approximately minus 0.00625. Remember, I need to get within 0.001. This next term is going to be plus approximately 0.0005. Well, that's it. This is the n plus 1th term. So that means I only need to go out to n, which in this case is 2. So this would be my approximation for that integral, accurate to, I know, within 0.001. And when I do my addition there, see, this is 1 over 24 minus 1 over 160, which is approximately 0.025, and I know I'm accurate to within that amount.